The deep learning revolution marks a major turning point in artificial intelligence history. Rather than introducing a completely new goal, deep learning transformed how learning systems are built and scaled. This video explains why deep learning succeeded where earlier approaches struggled. The objectives of AI did not change. Systems still aim to recognize patterns, make predictions, and support decisions. What changed were the methods, the scale of computation, and the availability of data, enabling far more complex models to be trained effectively. Early machine learning systems relied heavily on human-designed features. Engineers manually specified what aspects of data mattered, limiting flexibility and performance. These systems worked well in constrained settings, but struggled with feature engineering became a bottleneck. Extracting useful signals required deep domain knowledge and extensive experimentation. As problems grew more complex, it became increasingly difficult for humans to anticipate all relevant patterns in advance. Real-world data introduced complexity that exceeded what shallow models could handle. Images, speech, and language contained layered structure that simple representations could not capture effectively. This mismatch limited progress using earlier techniques. Neural networks offered a potential solution, but they were not new. Early versions existed decades earlier, yet they failed to scale due to limited data, insufficient computing power, and unstable training methods. From the 1950s through the 1980s, neural networks attracted periodic interest. However, practical applications were rare, and performance gains were inconsistent. As a result, neural networks were often set aside in favor of symbolic or statistical approaches. The failure of early neural networks was not conceptual but practical. Training deep models was slow, unstable, and computationally expensive. Without large datasets and efficient hardware, their theoretical advantages could not be realized. By the early 2000s, conditions began to change. Digital data volumes increased rapidly, computing hardware improved, and optimization techniques matured. These factors collectively enabled neural networks to be revisited under far more favorable conditions. Deep learning refers to neural networks with many layers. Each layer transforms data into increasingly abstract representations, allowing systems to learn hierarchical structure directly from raw inputs, rather than relying on handcrafted features. Depth allows models to represent complex relationships. Early layers capture simple patterns, while later layers combine them into more meaningful structures. This hierarchical learning mirrors how many real-world signals are organized. A key advantage of deep learning is representation learning. Instead of engineers defining features manually, models learn representations automatically from data, reducing reliance on human intuition and increasing adaptability. For example, image models learn edges, shapes, and objects directly from pixels. Speech models learn phonemes and words from sound waves. This ability to learn directly from raw data marked a significant departure from earlier methods. Neural networks consist of input layers, hidden layers, and output layers. Information flows through these layers, with each transformation guided by learned parameters adjusted during training. The term deep refers to the number of layers. More layers allow more expressive models, capable of capturing complex nonlinear relationships that shallow systems cannot represent effectively. Deep learning also depends on large data sets. Learning robust representations requires exposure to diverse examples. As data availability increased, deep models gained the opportunity to generalize better. The rise of the internet, digital sensors, and large-scale logging created unprecedented amounts of data. This data provided the raw material necessary for training deep neural networks effectively. At the same time, graphical processing units, or GPUs, became essential. Originally designed for graphics, GPUs excel at parallel numerical computation, making them well-suited for neural network training. Neural networks rely heavily on matrix operations. GPUs perform these operations far more efficiently than traditional processors, dramatically reducing training time for large models. As models grew larger, Infrastructure evolved alongside them. Hardware, software frameworks, and cloud platforms co-developed, enabling deep learning systems to scale rapidly. A pivotal moment occurred with the ImageNet competition. Deep learning models dramatically outperformed previous approaches in image recognition, drawing widespread attention from academia and industry. These results demonstrated that deep learning could achieve substantial accuracy gains when trained at scale. This success validated years of research and shifted the direction of AI development. Computer vision was transformed. Tasks such as object detection, image classification, and segmentation became far more accurate, enabling real-world applications previously considered impractical. Speech recognition also improved significantly. End-to-end deep learning models replaced complex pipelines, achieving higher accuracy and robustness across diverse accents and environments. Natural language processing benefited as well. Models learned richer representations of text, improving translation, summarization, and question-answering capabilities. Deep learning reduced reliance on handcrafted features across domains. A single model architecture could often be adapted to multiple tasks, increasing efficiency and reusability. Scaling became a central principle. Larger models trained on more data consistently achieved better performance, leading to systematic exploration of scale as a driver of progress. Researchers observed predictable improvements as models grew. These empirical patterns reinforced the idea that continued scaling could unlock further capabilities. As a result, AI research increasingly resembled engineering. Optimizing infrastructure, data pipelines, and training efficiency became as important as algorithmic innovation. Industry adoption accelerated rapidly. Technology companies invested heavily in deep learning, integrating it into products and services at global scale. Search engines, recommendation systems, translation tools, and voice assistants all began relying heavily on deep learning models to improve performance. Research culture shifted toward benchmarks and competitions. Progress was measured quantitatively, reinforcing empirical evaluation over theoretical elegance alone. New risks emerged alongside success. Deep learning models are often opaque, making it difficult to understand or explain individual decisions. Interpretability challenges complicate trust, accountability, and debugging. Even experts may struggle to diagnose why a model behaves as it does. Training large models is resource-intensive. Energy consumption, financial cost, and environmental impact became growing concerns. Deep learning systems are highly data-dependent. Biases in training data can be amplified, affecting system behavior across populations. High performance can mask weaknesses. Models may fail in unexpected ways when encountering conditions outside their training distribution. Despite impressive results, deep learning systems do not understand meaning. They learn statistical patterns, not concepts or intentions. Capabilities remain narrow. Models excel at specific tasks but struggle to generalize beyond their training context. Nevertheless, deep learning matters because it delivered sustained, measurable progress. It moved AI from promise to widespread practical deployment. Deep learning now forms the foundation of modern AI systems. It enables architectures that support large-scale learning and representation. Crucially, deep learning made generative models feasible. High-capacity representations allowed systems not only to recognize patterns, but also to generate new content. This shift expanded AI from perception tasks into creative and generative domains, setting the stage for the next phase of AI history. Historically, deep learning marks a transition from shallow, task-specific models to scalable, general-purpose learning frameworks. The key lessons are clear. Data scale matters, compute matters, and model capacity matters when aligned with the right infrastructure. At the same time, limits persist. Deep learning remains brittle, resource-intensive, and dependent on human-defined objectives. Deep learning should be understood as a powerful tool, not a complete solution to intelligence. Its historical significance lies in changing expectations. Progress became continuous rather than episodic. This sustained progress explains why deep learning endured where earlier AI approaches stalled. Next, we examine the generative AI era, where deep learning techniques underpin systems that create text, images, and other content, marking another major shift in artificial intelligence.